Oh, thanks. Hello? Okay. So before we get started with introducing the speaker, I just wanted to tell you briefly about this lecture series. This is called the Ohanian Lecture Series, and this is part of a foundation in honor of Jack Ohanian, who was a professor at the University of Florida here for over 40 years. He served as Associate Dean in our College of Engineering. He also served as Interim Dean of Engineering, also served as Interim Vice President of Research at our university. He was also a former president of the ANS, the American Nuclear Society. So Jack has left this legacy in this foundation lecture series. So I'm very honored today to introduce our college-wide Ohanian lecturer, Professor Cord Smith, who is a professor of practice of nuclear engineering at MIT. His expertise is in the area of computational reactor physics. He is also, in addition to his position at MIT, he's the chief scientist for the DOE Office of Science for the Center for Exascale Simulation of Advanced Reactors. In addition, he co-founded the U.S. branch of Studsvik. And Studsvik, for those of you who don't know, is a global leader in reactor physics software, which is used to license commercial nuclear power plants. He is also a fellow of ANS and a very active consultant in the nuclear industry. And we're very honored to have him here. Let's please welcome him.
Well, thank you very much. Is my speaker working? All right. All right. He's giving me a thumbs up. That must mean he's changing something. So, all right. Well, thank you very much for inviting me here. This is my first time to the University of Florida, and I very much appreciate the summer weather that you arranged for me. I grew up in Minnesota and South Dakota, so this actually does feel like summer to me, and I'm much more comfortable in this weather than I am in your summer. My topic for today is something I very seldom speak about in the future of nuclear power. I am a down-in-the-dirt computational reactor physicist working on modeling and simulation. So this gives me an opportunity to reflect over, I've been in this industry now for 43 years, so I'm looking back on things which I, and of course many, many other people have done. Now, there are people in the audience who would be much better at giving this talk than I am. Jim Telenko, of course, has probably given this talk 500 times in his career as the future of nuclear power has evolved over the last 50 years. But I'm going to take a stab at it anyway, and I'll probably be giving you a different perspective than many people. Let me talk just briefly about what I've done in the past, because it's a completely different experience from what I'm doing now. When I left graduate school in 1980, was a time at which we had anticipated building the Clinch River breeder reactor. It's going to be a large production fast breeder reactor, produce more fuel than it consumed, a concept which originated way back in the 1940s and 50s. And this was an experimental facility called the Zero Power Plutonium Reactor that I worked on for 4 years in doing analysis and experiments. And it's interesting because at that point in time, we didn't think anything at all about working with plutonium. Of course, we were safety conscious in what we were doing, but it was a different period of time. This configuration behind you has about 1,000 kilograms of plutonium, all constructed by hand by conscripts like me. When we were students, because you were allowed 5 rem per year exposure, and the technicians who would construct these things would get way too much exposure to do that, all of us rank and file employees who sat in front of computers all day were called on 1 day a year to come down and load fuel for these kinds of configurations. And we, of course, were so safety conscious we would allow ourselves only 3 rem per day exposure, and we got it all in one blast, year in, year out. So I have received, doing this work, more exposure than anyone Fukushima accident. And it's really strange when you talk to the general public that's so concerned about radiation exposure. We take it seriously, we monitor it, but we understand it to a great extent. And it's very, very hard to convey that to the public. So I like being able to tell that story because it's a risk that many of us are willing to take, were willing to take in those days, and I still don't know how to relate it to the general public. All right, so I worked there for 4 years, and then I went to work for a small Swedish company called Studsvik. 2 of us did what's now called innovation and entrepreneurship. We had no idea what those words meant. 2 of us got together in Boston and started a very small company. It's one of those things, if you've never done, you are going to work 100 hours a week for as long as it takes you to either succeed or fail. And failure is what happens to 95% of your startup companies. And it's a tremendous amount of work. It's also extremely invigorating to succeed. So we carved out a niche of developing software for the commercial nuclear power industry. It was all modeling and simulation computer work that I was doing. But in the process, I had to learn all those things that you need to know to run a business. So you are your own PR department. You are your own publications. You are your own lawyers. No one can afford a lawyer when you do a startup in those days. We didn't have, like now, a Bill Gates to give you $10 million to get started or $300 million to get started. It all came out of our pockets. It's very hard to do that. But it's very invigorating. And I spent 27 years working for Studsvik, enjoyed every bit of it. And then finally, at the end of this time, I ended up working out of our Boston office 5 years ago. And MIT finally convinced me to walk across the street and teach. They've been trying to get me to do that for a long, long time. And I have taught many courses on the side and enjoyed students. So I gave up being at Studsvik, where I was everything, chief cook and bottle washer. I was the CEO, I was information manager, and you have to do everything. But now back at the university, I'm back in detailed modeling and simulation. We're now trying to push forward ways of analyzing reactors we were never able to do before, because modern computing allows us to do an awful lot more. And so we are now trying to model these complex reactors where we individually will model every pellet in the reactor. So we're going to take 20 million pellets, and we're going to try to predict exactly what happens in each one of them. And of course, we're going to fail, because Jim knows perfectly well, none of us know what happened in every pellet. But we're trying to do simulations on that scale, so when Jim can finally tell us exactly what happens in fuel, we'll be able to do the modeling for all 22 million of the pellets in our large modern reactors. I also serve as chief scientist for the Center for Exascale Computing, and I'm quite optimistic about the future of high-performance computing. DOE believes and always has in high-performance computing, and we throw literally billions of dollars at high-performance computing. It's very difficult for us to wring performance out of these machines, and we're now in the midst of a big DOE project to build a billion-core computer. For any of you who've done parallel computing, you'll realize how difficult it is to get anything productive out of a billion cores from a single simulation. So it's a very big challenge. Students love it. It's got some great aspects to it, because we're trying to design software which can really run on all billion to simulate one thing at a time. And only, of course, in the weapons labs do they do that kind of thing. And computing has fallen off. It's only through massive parallelization that we're able to do computation of this scale. So that's just one of the things that my students do, and that's not what I'm going to talk about today. I would love to talk about reactor physics, critical experiment analysis, cross-sections, modeling and simulation, but that's not what I've been asked to do. I would also love to talk to you about what I do for my hobbies, which is flying. And someone pointed out to me that I'm not qualified to talk about risk, because this is an airplane I fly. Oops, I guess I shouldn't have touched something.
Just touch the screen again.
Okay. All right. Has anybody seen the James Bond movie that has flown that? This is what I call Death Wish 1, is that airplane. This is my other airplane. I fly into the Idaho wilderness, backcountry flying, land on 500-foot mountaintop strips with that airplane. So when I tell you something's acceptable risk, take it with a grain of salt, what that might mean to the average person. Okay, so I am actually going to talk about a brief walk back through my view of the commercial history of commercial nuclear power, the role of nuclear power, and what the future might look like for that. So, Now, I'm going to go all the way back and do the real quick march through the 1950s, 60s, and early 70s, because it has a big impact on what is wrong today, in my view. And I hope by the time I get there, you'll understand what I mean. And I'm going to punctuate this history with 4 accidents that have happened, that have had a tremendous impact on, in both good and bad ways, on nuclear power. Okay. All right, where did we all start? Not too many of you were alive, other than the first row here, in 1950. And nuclear power, of course, started out from the negativism of the 1950s and the early Cold War, where everybody was worried about nuclear weapons. Even I, as a child, learned the duck and cover in school that we taught, just like Pledge of Allegiance to the flag was how to get under your desk in the case of nuclear war. And can anybody possibly imagine what good that could have done? But, every public building was fallout shelter. In the basement of public buildings. I actually had a summer job one time inspecting fallout shelters. And then some people, of course, went so far as building their own bomb shelters in their backyard for this inevitable collapse that was going to happen. But that really wasn't the picture of the 1950s. Of course, I was so young, I don't remember it that way. But it really, with President Eisenhower's 1953 address at the United Nations, the so-called Atoms for Peace talk, and later in 1954, the Atomic Energy Act, which authorized civilian use of nuclear power, really set the stage for what I think was the real thing that happened in the 50s, and that was there was actually incredible optimism in the 50s. And in fact, in nuclear power, people talked about everything, from the Ford Nucleon car, the nuclear-powered train, the nuclear-powered airplane, and of course, submarines and ships, which actually happened. So people had a natural optimism, and things were changing so quickly in the 1950s. It was a dynamic time. I'm sure for young adults, I was much too young for this at the time, but the speed at which things changed was tremendous. It's kind of like all across big industry at that time, things were changing, like perhaps they are now in the IT world, where every 6 months there's something new. You gotta have the latest iPhone. But big industry was changing very quickly in the 1950s. So it was a great time. We didn't think much about radiation at the time and the way it is now. You gave your kids polonium-210 to play with, the same stuff that the Russians have used to kill the spies that they don't like. That was toys for tots. It makes great cloud chambers if you've got a good alpha emitter, right? It was a different time. You could go in and see how well your shoes fit with a fluoroscope. And you even made it so your parents could both look into the fluoroscope at the same time to see in effect, an X-ray of your feet to see how well your shoes fit. It was a different time. In 1951, in Idaho, at the Experimental Breeder Reactor number 1, produced the first power, which was really only 4 light bulbs at the time. And this was, it's amazing to me to look back on this, because this is a sodium fast reactor capable of producing more fuel than it consumed, cooled by sodium, a pyrophoric metal coolant. And this was all done in 1951. And the people who built this facility design reviews, construction, it all changed dynamically while they were building it. They didn't sit around and do paper studies for 10 years to figure out how to build this reactor. They had a plan, they started out, they changed as they went, they learned from mistakes. And things happened quickly. And it was a really, really important dynamic at the time. By the way, this picture, does anybody know what these 2 big blobs are sitting out there? Anybody believe that those are engines built for the nuclear-powered aircraft? In Idaho, there's such a hangar, a runway, and 2 engines that were built to power an airplane that in early 1960s would have been capable of flying around the world nonstop 3 or 4 times. A propeller-driven plane in 1961 that could go 250 miles an hour, completely useless, and fortunately was killed in 1961 when President Kennedy took office. But it's one of the things I like to use as an example. We as engineers, if you ask us, can you do this? Sure we can. But That's very different than asking the question, should this be done? And as engineers, quite often, we really need to stand back and answer kind of some social questions along with what we're being asked to do. Even if it's possible, yes is not always the right answer. Some questions should always be answered no. So, obviously, the Navy in 1954 launched the Nautilus Submarine, which really was the culmination of a tremendous amount of research. The best people in the world worked on nuclear power in the early 1950s. And the prototype for the Nautilus was constructed in Idaho, operated 1954, 1955 for the first time, sailed under the Arctic Circle, I think it was 57 or 58. Tremendous things were achieved. And this had a huge impact on commercial nuclear power because the very same type of reactor, the pressurized water reactor that went into the Nautilus, was later deployed for civilian power. A very exciting time. In 1958, the Naval Reactor Program helped construct the shipping port reactor for the Duquesne Light Company. Has anybody heard of the Duquesne Light Company? Pennsylvania? No, I'm sure it's not around anymore. But there's a reason it was called the Light Company, if you think about it. In 1950, there were a lot of places just getting electricity for the first time. I lived in a house in Minnesota that got running water in 1968. It had its first indoor toilet in 1968. So there's a reason they were called light companies, because many places when they got electricity, that's all they did, was they had light bulbs in a couple of rooms. And so there was this huge push, and it started before the 50s, obviously, in rural electrification, and cities had been there before that. But you have to remember that even the US was in some ways a third world country by today's standards in 1950. And you don't go from being a third world country to a first world country without doing some incredibly progressive engineering and deployment of huge systems. And electricity generation is one of those. I like this example. It's a very obscure reactor. In 1962, the Elk River Reactor was built in Minnesota, my home state actually. And it turns out there was already a power plant there, and they built this nuclear plant basically as a preheater for an oil plant. There was only 20 megawatts electric, and it was built. But the reason I like this example is it was a different reactor type. It was a boiling water reactor. At Oak Ridge in 1965, they built the Molten salt reactor. And it had liquid fuel, molten fuel, mixed with molten salt to be the coolant. It was an incredibly diverse set of reactors being built in the 50s. There were, I'm not sure the number, but probably of the order of 50 different reactors built in the decade from 1950 to 1960. In fact, in Idaho over the years, there were 42 of them built at what used to be called the National Reactor Testing Station. But the reason, I've got one more before that, I guess. I wanted to bring up one different type. Peach Bottom in 1966 was a commercial electricity producing reactor, graphite moderated and helium cooled. So here we are. We always think of water as our coolant, and it's what we use in most reactors today. But from the earliest time on, we had sodium, we had helium, we had coolants of all types, reactors of all types. And the people who built these things, if you could dream it, you could do it then. And it took literally a couple of years to go from a concept to a functional plant. And this Elk River Reactor I use as my example because it was built by the Allis-Chalmers Company. Now, how many of you know Allis-Chalmers? Some of you should. Anybody that's been in farmland knows Allis-Chalmers, right? Allis-Chalmers at the turn of the century was building power plants that looked like this. In the 1950s, people who could do this had the optimism and creativity to do that and not be intimidated by nuclear power. It's just another teapot. It's another way to boil water. And people looked at it that way, and they built them. And Allis-Chalmers, at that time, this was their main product, was a tractor. And yet, they were willing to take on financial risk to do this. They, of course, failed in this case to ever produce. They produced two reactors that I know of, the Pathfinder reactor in South Dakota and the Elk River reactor in Minnesota. They were going after rural electric, where you didn't have big power plants. They were going to produce small power plants in rural America. But I like you to remember the mindset of these people, that it was a can-do time when, if you could think about it, you could find the money, somebody to supply the money to do it. And of course, the government at that time did actually supply a lot of money for these first of a kind plants. They went out and did it. So, all right. So anyway, I like to think of the nuclear industry in the 1960s as just like the automotive industry was in the 1910 or 1920 period of time. There literally were 1,000 companies manufacturing cars at that period of time. And of course, all but a dozen of them went broke in the next 10 or 20 years. But it was the same kind of thing. Every concept you could think of was being tried. It was being shaken down. You went through very rapid deployment and testing. You proved what was or was not feasible quickly. You learned from your mistakes. You crossed some off your list, and you moved on. And that's exactly what happened in the nuclear industry in the 1960s, at least from my perception. The Atomic Energy Commission supplied startup funds, and at that time, I think I would argue that the nuclear industry had the intellectually best people in the world. If you were anybody, you wanted to be working on nuclear power, because it was the happening thing in the 1960s. But the one thing I come back to, and I think about it every time I look at a US government project today, the reason things worked back then is people were engaged and construction times were short. So you could move into a project and see it through to completion personally. We had people who did design, construction, operation. You didn't just do one thing. You were integrated in a giant project, and you cared about all aspects of that project. And that's something that I think is dramatically missing today. We each do some small piece, and we don't take ownership of the whole project. And I don't think it's at all unique to nuclear energy. And on the university front, of course, many programs, I'm not sure what year you started here, it must have been early 60s. There were a tremendous number of educational programs started at that point in time, drew tremendous faculty from around the world to staff them. All right, 1970s, a lot of things happened in the 1970s, and they weren't all good. It's kind of like landing on the moon in 1969. I keep forgetting that most of you weren't alive when US landed on the moon. But most people don't remember 1973, who weren't around then. But the oil embargo of 1973 made a profound change in energy in the United States. The cutoff of the oil supply to the United States from the Arab republics led to a shortage of oil in the United States, drove up tremendously the price of oil, and for the first time we felt a vulnerability. Can anybody tell me what the price of oil was in 1973 before the embargo? What was the US paying the Arabs for each barrel of oil taken out of the ground?
$3.
Yeah, $2. $2 a barrel is what we were paying for that oil. And yeah, we were taking advantage of them. But that sent a ripple through the entire US economy, which I'm not even sure you can measure all the ripples from it, but it had a lasting effect. Immediately after that, the US government recognized the situation and split up what was then the Atomic Energy Commission into two entities, the NRC, Nuclear Regulatory Commission, for the regulation of civilian power and everything else nuclear in the US, including things which cause you trouble here, I guess. And then ERDA, what was the Energy Research and Development Administration. That move, which seemed to make sense at the time, I argue was the single biggest mistake that the United States government ever made. Because we used to have people who worked simultaneously on both of these items, not one side of the fence. We had people who moved for a period of years to work for the AEC because they felt an obligation to contribute to that. And now all of a sudden we formalized regulation from development. Scientists didn't want to be involved in regulation. They wanted to be involved in development. So we fractured the intellectual community across those lines. Early on, it wasn't quite as prevalent as it became later, and it's actually improving today somewhat. But I argue that that was a big mistake. I mean, from a safety point of view and a public perception point of view, it's a good thing. because NRC has credibility, which industry in many cases lacks. But I think in terms of where it left us, it probably was a mistake. ERDA became DOE a couple of years later. The other thing which permeates everything is the growth of the green movement in the United States. Everybody, my generation included, was an anti-disestablishmentarianism. It was the ticket that you had to be against something, right? And everybody was against the war in Vietnam. I tried to volunteer to go, but they wouldn't take me. But most everybody, all my classmates, were against the war. It was a big focus, and it evolved into some good things. The energy movement ended up being good, but at the time, you had to be rabidly anti-nuclear if you were green. There was no other way to it. And nuclear energy, I think, became a focus almost by accident. If nuclear energy had been 10 years ahead and already fully deployed, we might have missed part of that. If we'd been 10 years later, there would have been something else for the movement to be against, and we might have come in without that. But we were in the wrong place at the wrong time, and we were a focus from that. And then the really thing that hit us in the late 1970s was rampant inflation in the 1970s. And if you look, historically, the interest rates had been 6 or 7% historically. And this is plotting if you got a fixed rate mortgage, what it would cost. There was a spike right after the 73 oil embargo, where if the prime rate that you are going to borrow money for your project follows prime and it's 12% interest. Who'd take out a 12% interest loan today? Anybody? No. See here in 1979, 1980, peaked at 20%. I took out an 18% house loan. Was I out of my mind? I mean, you have to live through the times you are in. And it actually, believe it or not, made sense to take out an 18% loan because housing prices crashed. Not like kind of like 2007, 2008. When the downturn came, prices came down and there still was an incentive to buy, if you could, borrowing money at these ridiculous rates. Now we sit out here today and we're beginning to think that 3 and 4% money is the norm. When I plan a big project and I look at that curve, I don't think 3 or 4% is what I want to be basing my interest rate on for my decisions going forward. But I'm not sure how to look at that curve and make any sense out of it. What is history telling me? All it's telling me is I better understand financial risk, if nothing else. All right, nuclear power, we're starting to deploy in the early 70s. I think when I started undergraduate nuclear engineering in 1972, there was nothing but exponential curves upward lying in front of us all. We were going to have 500 reactors in the year 1990. And we were literally building 100 of them in the 1970s. Huge numbers were being built. But when this happened and inflation hit these levels, it had a tremendous impact on a project which takes 7 or 8 years to build. That interest rate killed so many projects. And then in addition to that, lots of projects were naturally running over cost on their own, compounded with the interest rate. There were probably, I'm not sure, Jim, you might remember the number, probably half to 2/3 of the reactors on order were canceled in the late 1970s, driven largely by interest rate problems. Okay. So we get all the way through the 1970s. We're starting to get lots of these plants are coming online, and 3 Mile Island happens. Now, student-wise, how many of you, well, you probably can't remember 1979, right, at all, but do you study 3 Mile Island in your coursework of what happened there? And it's a very, very interesting story, and we learned so much from what went wrong at 3 Mile Island. It's a complex sequence of seemingly unimportant events that ended up causing a major catastrophic partial meltdown of this core. And that's one part of the story. But the bigger part of the story is actually how it was handled by us and by the public. We were not geared up for accidents. We didn't know how to talk to the public. We lacked information while this was unfolding for numbers of days or a week. We couldn't actually say this is exactly what is happening at the plant. And that became very obvious to the public. And there was lots of accusations about the utility that was operating 3 Mile Island. They weren't being forthcoming. They weren't telling us the truth. How can we trust people running these plants? That, and also, as I was mentioning earlier today, the cooling tower became the symbol of nuclear power for some strange reason because of 3 Mile Island. If you put up a cooling tower and ask somebody, what is this? They'll tell you it's a nuclear power plant. It is our symbol. So anyway, 3 Mile Island happened, and there were a lot of, in the end, positive things that came out of it. One of the things was we learned the importance of human factors in the operation of complex equipment. Okay? We had to factor that in. Probabilistic risk assessment, which we were in the middle of the first really big study, the WASH 1400 study that Norm Rasmussen at MIT was leading at this time, had largely identified all of the faults that were going to unfold at 3 Mile Island, but had done nothing to fold in the human factors aspect because that wasn't really part of the game at that point. We had picked up large pieces of probabilistic risk assessment. Now, obviously, everybody calls it probabilistic safety analysis. I kind of detest that in the sense that it's, yeah, maybe the public wants to hear that, but you actually go through the sequence by looking at risks. You don't go through and say, what's safe? You ask, what's the risk when you do it? But anyway, the other thing is understanding financial risk. It's not just what does it cost you to build this, what does it cost if interest rates aren't what you assumed, if something goes wrong, but this is if you lose your entire investment and incur a huge financial penalty. That needs to be factored into every large project. That probability that something really bad is going to happen financially. Okay? I mentioned public communication and distrust of company officials. I think that was solidified. You can read about it to this day. There are people, even though the actual exposure releases at 3 Mile Island were unbelievably low, you can go out on the internet and you can find any number of people claiming that hundreds of thousands of people have died as a result of 3 Mile Island. It's complete nonsense, but we have a forum which allows us to publish anything we like without peer review, right? That's the beauty of the internet. I can do anything I want. It doesn't have to be credible. And of course, with that is public acceptance is important. And it's very difficult. That's part of the reason I don't go out and publicly speak, because I have never learned a good way to come across to the public. I tried this in graduate school, and I was telling students this earlier today at the time of the Seabrook plant being built in New Hampshire. I would go to the public meetings. As an MIT student at the time, we would talk about it. And Helen Caldecott, who was one of the most rabid anti-nuclear people around at the time and a credible physician, would to our face call us baby killers because we were promoting nuclear power. And that is the image that she wanted to paint for anybody remotely involved with the industry. We were not credible people. So that's something that's very hard to deal with. Okay, the outgrowth of that, there was, obviously I mentioned human factors. Emergency planning improved tremendously after 3 Mile Island. We went after it with a vengeance. The NRC put inspectors at every power station because part of the problem at 3 Mile Island, there initially was no government presence for the first, I don't know what it was, Jim, 3, 4, 5 days until somebody from the NRC was on site to sort of become the spokesman with some credibility independent of the utility. That's now an institution at every plant. Obviously, radiation monitoring was proved to be one of the problems there. They weren't really set up for monitoring a release because we weren't planning on releases. And it turned out there weren't very many, almost nothing significant was released, but we didn't have the information to prove it. So now you see really good monitoring equipment. The Institute for Nuclear Power Operations was created very shortly after 3 Mile Island. It's a very influential industry group. And part of their mission is simply to share information on what happens at every plant with every other plant. Because the things which preceded the events that I won't talk about at 3 Mile Island had actually already happened in other plants, the individual events. And if that information had been deployed across the spectrum of plants, it might have avoided what happened at 3 Mile Island. Now, 3 Mile Island was really bad. And the things that happened there are interesting to analyze now, 35 years later, and I used this example. I'm sure you've all read about the 2009 crash of Air France Flight 447, which killed 228 people. This was the flight from, I think it's from Brazil to Paris. That perfectly flyable airplane was flown right into the ocean because of exactly what happened at 3 Mile Island. They had a small mechanical failure. The pitot tube, which measures the velocity of the airplane, was frozen over because of poor design with ice crystals. Once it was no longer getting its signal, the autopilot turned itself off. The pilot then had to fly it. He was perfectly capable of flying that airplane, but he had one instrument telling him his speed was 0, he had another instrument telling his speed was something else, and the whole situation devolved. And it's the middle of the night. It's pitch dark. You can't see the horizon. In an airplane, if you can see the horizon, any fool can fly an airplane if you can see the horizon. But when you can't see, what you feel is completely deceptive in an airplane. You can go through a complete spiral dive and feel like you're perfectly balanced because the way the inner ear works. They didn't do that, but they didn't realize that they started to pitch up, and because their airspeed indicator was not working, they got pitched up, pitched up, pitched up. Finally, they got a stall warning. Well, they thought they were still at a different attitude, and so they pulled up even more. And they finally stalled out at 38,000 feet. And for the next 3 minutes, the pilots never realized that all they had to do was point the nose back down. The thing you learn in your 5th hour of training in any aircraft, private or otherwise, that to recover from a stall, you point the nose down, you get up airspeed, you fly right out of it. They held the nose up as much as 30-degree incline for 3 minutes, flew it all the way to the ground, to the ocean, sorry. And of course, everyone was killed. So my point of bringing that up is, they could have learned from the 3 Mile Island lesson. They didn't train for the right scenarios. They've got the best simulators in the world in the aircraft industry. They could have trained for this scenario, and they didn't do it. And they paid the price, or everybody did, for that lack of training. And so I argue what happened at 3 Mile Island is in no way unique. It will probably happen again. It's almost human nature. When things don't go right, they can go very wrong, even though your device is perfectly functional. 3 Mile Island reactor basically had one stuck open valve. And if they had had the right instrumentation, which has improved tremendously since then, they could have easily recovered from that event. All right, I don't want to belabor that one. Let's move on to the 1980s. I call this the stagnation of commercial power. Because of the high interest rates, many plants were canceled. There were no new orders. Congress canceled the Clinch River Reactor. Remember, this is a time at which we're professing as a nation to really be seriously concerned about energy, right? We've had the oil embargo, we're on our mission. We've reinvented ourselves every decade of getting reinvigorated about energy, and I argue the United States government is the least effective entity in energy that we will ever see, that we're just not able to sustain any momentum in one direction. Clinch River, of course, there were huge cost overruns, and it was canceled by Congress in 1983. We slowly completed the last of those plants, but there were some positive things that came out too. The full scope operator training simulator is now deployed at every power station in the country. If you're going to operate a plant, you have to have a full scope simulator. You walk into a room, it looks exactly like your control room. It's all simulated by software. But operators spend tremendous amounts of time. Most of these facilities operate 24 hours a day, 365 days a year, training somebody for all those scenarios that we hope never happen. Okay? All right, so in our tradition of shooting ourselves in the foot every decade, along comes 1986. The Chernobyl accident had a tremendous influence. And to put this in context, you have to realize, if you weren't alive in 1986, that basically there was no direct communication between the United States and the Soviet Union in 1986. Finally, when the Berlin Wall fell in '89, things mellowed out and we actually really had interactions. But the Russians basically did their own thing, and we looked the other way. We knew perfectly well that that was an unsafe reactor by design. There were no great secrets about that. It had no containment building at all. And when this accident happened through a complicated sequence of events, which should never have occurred, it had an steam explosion / fire, and released a giant plume of radioactive material. The whole core basically disassembled, and it was launched over Europe. And for 2 days, the Russian government said nothing. It didn't tell the city of 50,000 people living right next door that there was any problem. They brought in firefighters, obviously, to fight, many of whom died as a result of radiation exposure. Some 30 to 60 people died, very short-term radiation exposure at Chernobyl. Nothing was said by the Soviets until at the Forsmark reactor in Sweden, because of their monitoring equipment at the site, they picked up a plume of radioactive material showing up in Sweden. And only then did they figure out what had happened, and the Soviets got called to task and admitted what had happened. They then evacuated people from the town around there who had already been exposed to large amounts of radiation. And it was a tremendous explosion. I love this picture of a 2,000-ton steel lid that was setting on something after that explosion. Completely ruptured the core. Material went everywhere because of the lack of containment. Okay? So what did we learn? The main thing we learned is it doesn't matter what plant has an accident anywhere in the world. It is all of our problems. We are all going to pay the price for when that happens. We should have never accepted poor reactor designs or lack of containment buildings. Now we see international standards being applied. But when you back up to that reactor and see it destroyed, there's 3 more of them sitting right here. They all operated for another decade after that accident, right in the middle of the largest contaminated radioactive zone in the world. They kept operating. They needed the power. And that's part of the reason the Russians built these. They were basically infinitely scalable. They were cheap to construct. You could do it all with local construction. And as a result, we ended up with this RBMK reactor, of which there will never be another one built. All right, let's move on to the 1990s. We finally get to the modern era where we now care about greenhouse gas emissions. And we finally get some focus on this. We're seeing that CO2 generated per year is going up exponentially, especially from electrical power plants. Electricity is one of the biggest generators of CO2 out there. We think about cars, right? I mean, we kind of don't have a lot of choice at the moment other than burning carbon in cars. But in electricity, we've got other choices, and nuclear is one of them. But we're seeing this huge growth in anthropogenic CO2 production around the world, and people start to focus on it. And obviously in 1997, the Kyoto Accords were signed, and we're all in agreement that we're going to reduce our CO2 emissions. At least we say we are. And what's happened is we have some other players. China comes in terms of energy generation. This is just when they take off, right after the 1997 Kyoto Accords are signed, and they are exempted from the Kyoto Accords because they're a third world country, right? You cannot tell people not to dig your way out of my 1950s version of having no running water. They have to get from way down here to way up there with more than 1 billion people. So yes, when they pull themselves up, they are going to have a tremendous CO2 generation, and they get a lot of it because of coal. There are so many coal-fired plants being built routinely in China to supply the electrical energy needs that they are now the largest CO2 producer in the world. They will outstrip all of the other developed countries in their rate of growth of CO2 production, and they're almost making it immaterial what we do in the United States to reduce greenhouse gases, other than, I would argue, the positive effect we could have by doing something proactive about CO2. All right. I like this chart because it shows China way down here in terms of greenhouse gas emission per person. They're way down here. They're actually really, really good. They're a 5 times better global citizen than we are, right? I mean, per person, they're not doing much. Now, the integrated area under the curve is how much they're doing, and they've now passed us. So as they come up anywhere close to our standard, and they're on that growth curve to do it, what's going to happen? We are going to have a tremendous amount of CO2 produced. No. All right. Well, they are building plants. They've got 17 gigawatts of plants installed capacity in China now. Most of them built originally by foreign companies, except one. I was there in 1988 and went to visit the Qinshan plant before it was ever operating. It's very interesting. I went to a building. It's got 5,000 engineers. It's got one room with heat. This is Beijing in December. It's got one room with heat for 5,000 people. It has 5 telephones for 5,000 people. It has no computer. It has no telefax. And they're building a nuclear reactor. And you know what they built? They stole an old design from Westinghouse and tried to replicate it. Pencil and paper. And they built and are operating that plant today. Okay? And then, of course, the French came in and built a bunch of plants for them. The Russians have some. The AP-1000 is being built there. There are now 40 gigawatts electric of nuclear power under construction. Now, if we had 40 gigawatts being constructed in the US, we'd say we're doing something, right? But 40 gigawatts in China barely shows up on the radar screen because of the rate at which they're having to add electrical capacity. So it really is hardly making a dent, even though in their long-term plan it will. All right, we finally get to Fukushima, March of 2011. Next major problem, and I'm sure you all followed this one. Is there anybody who slept through Fukushima? Okay, I'm glad to see that. Well, anyway, it was a devastating event. I'm actually kind of appalled when I go out and look at the internet now and I search for Fukushima Tsunami. Do you know how far down that list I have to go to see anything about 25,000 people that died? Yeah, I got to be 30 hits down. The first 30 are all about what is going on in nuclear power at Fukushima. No one has died. I've had more exposure than the most exposed person at Fukushima, and yet it is daily news what's happening at Fukushima. And of course it was devastating. And I know probably not very many of you have been to Fukushima, but every Japanese site is the most beautiful place you will ever go. They manicure the lawns. They have the cleanest reactors you've ever seen. I've spent probably a year of my life in Japanese reactors. They have very conscientious people. They know their facilities like we do. It's not that they didn't know what they were doing. But you notice the 5-meter seawalls out here. When this tsunami comes, you're going to watch what happens across this plant site. 4 reactors, units 1 through 4 are the big block buildings. And when the water comes ashore there, you have a 15-meter wave coming ashore across a seawall designed for a 5-meter maximum height tsunami. And bad things happen. You notice the water starting to flood in around the equipment, and watch this tank. In the next picture, you see the very same tank, and this is actually quite a ways into the plant site, almost buried in water. Now picture yourself in the control room at this point in time. Obviously, you don't have picture windows in control rooms. They're protected from the outside. Now all of the electrical switchgear is underwater. You've lost all of your AC power, either because of the earthquake, which is a 9.0 Richter scale earthquake, one of the largest ever recorded. They have no off-site power. They flood their DC batteries, which are supposed to last for 8 hours. They have no power. Now, I don't know how many of you have ever stumbled around in your house when the power goes out and just try to walk down the stairs and find something. But imagine yourself in a complex power plant trying to find your way around in the absolute pitch dark with massive amounts of water. It was an impossible situation that they were in. At this point, the plant was pretty much doomed. And this happened 45 minutes after the earthquake, that the tsunami came ashore. So, and when we look back through the accident, very little damage was actually done at the plant. There were, 1 crane operator was killed in a collapse of a crane. There were a couple of people at Fukushima, operators drowned because of the water. There were 3 people at the Fukushima site killed. But there was a cascade of sequences of things went wrong at Unit 1, and they lost their water cooling because they had no power. They started to uncover the core. They got a zirconium oxidation reaction, lots of hydrogen produced. Ultimately, some time into the accident, there was an explosion. Might have been 11 hours. A lot of this is estimated on some of the individual things which happened. But 2 other reactors for 3 days, they were successful in operating those reactors and keeping them cooled. But they still couldn't get off-site power. because everything around the plant had been destroyed. And it was 11 days before they got any help from the outside with power. So eventually, even after the 3 days, it wasn't designed to go this long without external power. It has no diesels. They were all flooded. They hung on for 3 days, and then they lost those two. They couldn't keep them covered, and then they had what we all witnessed, which were the hydrogen explosions. And this, for any nuclear engineer that's ever done safety analysis, is the most heart-wrenching thing you will ever see, is an explosion of that magnitude. And yes, it's just hydrogen gas. It's not a nuclear explosion. But I mean, you could see the shock wave from that explosion. It was a tremendous explosion. And then there was the second one, or the third one, very similar, a little bit smaller, and left this kind of structure at each plant. Totally destroyed the outer buildings, damaged the internal containments. But unlike Chernobyl, almost all of the containment structure was still intact here. So even though you've melted the core, and then ultimately they've probably melted through the bottom of the steel vessel, we do not have the magnitude of release that you had at Chernobyl. You've got 4 reactors, and you probably had a factor of 10 less total release than at Chernobyl. That containment building still served a tremendous function for us. Oops, that wasn't good. All right, so what did we learn? The main thing I think that came out of this was that this was a complete failure of your design basis. Now, I don't care what piece of equipment you build, you have to decide what is the design basis for this equipment. You build a car. Does the car passenger have to survive a head-on impact at 100 miles an hour with a semi? No, I guess we're not going to do that. Does an airplane have to crash with no people killed? No, you can't build something if you demand absolute risk-free operation. So you have to decide a design basis. And here the problem was that lots of mistakes were made in choosing the 5-meter historical height for a tsunami, when there was some very, very old evidence from hundreds of years ago of tsunamis of larger magnitude. Now, if you look just 20 kilometers to the north at Fukushima Daini, it has a 13-meter seawall. It's 20 miles away, 20 kilometers away, and yet they had a different seawall height. So there were tremendously bad decisions made in choosing the design basis. But remember that when you design anything, as soon as you say, I know the design basis I'm going to design to, if anything happens that goes beyond that design basis, you are not protected. And in their case, this went beyond design basis. The water should not have come over the seawall. It did, and all of the planning in the world didn't save them from inundation of the electrical systems. Okay. All right. Compounded that was off-site problems. Multiple unit events were not normally analyzed. We think about having an accident in one plant, not an accident simultaneously in 4 plants. It was unbelievable that that happened. And now we have all had to change the mentality which we do these things. You'll see much discussion, and I'm actually not very involved in this, about how they lacked decision-making ability on site. Lack of local command. They needed to get approval to do things. That's what their procedure said they should do. And Japanese are very procedure-oriented people. It's both good and bad. But in this case, they would try to get permission. They didn't have communication, lots of problems, decision-making on the other end. Unlike a submarine, where there is a person who can make a command decision on a submarine. Right or wrong, you're going to get a decision. And then the need for off-site response. And that's the thing you're seeing being rethought around the world now, is how do we move in from great distances, support very quickly for this plant? So you're going to see that. All right, I'm going to not spend much time talking about dose rates. They've come down tremendously, but still we are talking about dose rates in the vicinity of the Fukushima reactor that at least from what I see, there are roughly 5 rem per year. And I use the 5 rem per year, which is the kind of the heavy yellow here. That's the occupational safety limit in the United States for a radiation worker, 5 rem per year. I'm allowed to get 5 rem per year and go on about my business. Well, nobody's going to be allowed in the Fukushima prefecture to return at 5 rem. The natural background is 0.2 rem per year. So I think until that radiation is down to 1 rem, there will not be a decision, even though there's not adverse impact to doing so. You cannot make a political decision in the current environment to allow those people, there's roughly 80,000 people not able to return to their home. Until they're allowed to go back, this accident is never going to be over. And that's one of the big things that's different from an airplane crash. 229 people were killed. The next day, there's not going to be another fatality. You have a tsunami in the Indian Ocean, kills 300,000 people. Well, okay, 300,000 were dead. But it's over. It's done. This is not over. And that's the one that you can't see it, you can't smell it, you can't touch it, and it's not over. That's one thing that's very different for us. All right, I'm running out of time here, as I always do. I keep saying I have only one time period. I know how to talk for an hour and a half. Doesn't matter what you ask me to talk about, I talk for an hour and a half. I just want to very briefly say about the future, because it isn't all negative. I don't want to just talk about accidents. We see around the world, France is always our example for nuclear power because they get like 75% of their electrical energy from nuclear power. But let's look in the US at how old our plants are. Most of our plants have now gone past their 40, or they're planning for more than 40-year life that they were designed for. Most are approved for 60-year life. But even at 60 years, they're not going to last forever. You're going to have to replace them with something. And you're not going to replace all of them with windmills, even though we're trying very hard. If we look around the world, the Finns were the first to order the new European pressurized reactor, and this was hailed at the time, pre-Fukushima, as a really progressive thing. It's going to be the first of the new plants built. Unfortunately, they are now 7 years behind schedule and at least a factor or 2 over budget. We cannot survive that kind of economics in the current environment. And the Finns are some of the best people at building things. Their operational record with nuclear plants is second to none. Their outage intervals are the shortest of any plant for refueling. They're incredibly procedure-oriented and good at it. Westinghouse AP1000 reactors are a much simpler reactor than the EPR, and that's one of the problems with EPR. They opted for active, redundant safety systems. That adds construction complexity. It adds piping, it adds electrical. The Westinghouse AP1000 system goes in another direction for passive safety to get around some of those problems. And we're seeing now, we're very near completion in China of the first of the AP1000 units. We have plants at Vogel and Summer, which I'm sure many of you can relate to here. They're well under construction. It is going to be critical to see that these plants are finished on budget and on time. That has to happen for the next generation of plants to be ordered in this country. And so we're all watching very, very closely what happens at these plants. And part of the reason I say that is we got to look at the competition. If you look at a combined cycle gas turbine plant today, and this is a picture of a 900 megawatt, that's almost the same size as your AP1000 reactor. It has this one has 3 large, basically turbine engines connected to a conventional Rankine cycle. They're now 60% efficient. They have marched slowly forward in this incremental improvements in efficiency to where that plant can be ordered, it can be delivered in 18 months, it can be run by 25 people, it's 60% efficient, and gas costs $3 today. And under those conditions, there is no source that can compete economically with that. Wind can't, solar can't, coal, oil, nothing can compete for that cost. So here we are at $3 a million BTUs for gas. But if we march back to 2008, it was $13. Now I'm trying to figure out what plant I want to order. If I'm ordering in 2008 and gas is $13, how can I possibly make a decision that's going to be right when gas is $3? Or what worries me more, if I'm sitting here today making a decision on $3 gas and it's $13 next year, am I going to be in trouble? And you will be in trouble at $13 because almost all your cost on this plant is gas. So, let's look at oil. Crude oil prices in the 2000s have gone all over the place. And for the first time in history, we have a sustained price of roughly $100. Okay? That has never happened before. We have had spikes in '73. We have a spike here. In fact, I think I have a picture. Yeah, if you go back and even inflation adjusting these things, in 1979, we were paying $115. Okay? The '73 oil embargo really only pushed it up to 40 or 50. But we're sitting out here today with oil prices where historically you would say the inflation adjusted price should be $30 a barrel. Okay? Well, is it going to stay at $100 a barrel? Can gas possibly stay at 3 and oil at 100? I argue that that's absolutely impossible. The energy content of those fuel is so easy to see that if they both stay there, I'm going to start taking this natural gas and make liquefied petroleum products if oil's going to stay at 100. So one or the other of those has got to change. We know that's going to happen. But how long is it going to take to happen is what we don't know. Okay. And then I go back to our cost of money. This has to be rolled in again and again with every decision we make. So, and I argue, even though I love being able to borrow money at 3%, it's not going to stay there. All right, no discussion could be ended without talking about the debacle of Yucca Mountain. It is the stone around our neck in the nuclear industry. What are we going to do with nuclear waste? And Yucca Mountain, in 1982, the Nuclear Waste Policy Act said we will have a repository for utilities to get rid of their fuel by '87, and it was supposed to have been opened by '98. And it's a giant hole in the ground in the middle of nowhere. I love middle of nowhere, that's where I grew up. And it's just a big underground storage dug into a mountain. It's kind of a simple technology. I'm not sure how you can spend $20 billion doing this, but we managed to dig a $20 billion hole in the ground that we're not even going to use now. So a political decision was made that, no, this is not acceptable. And there are some reasons for that, not all technical, mostly political. But when I stand back and look at this from a risk point of view, do you know what lies just to the east of this, of Yucca Mountain? It's the nuclear weapons test site. The Nevada test site is right next door. There have been 1,000 nuclear weapons detonated at the Nevada test site. This happens to be a picture of one of them where we, in the early days, were crazy enough to believe that we were going to do excavation with nuclear weapons. And so we decided to blow a big hole in the ground to prove that we could move dirt. And you did this 65 miles from Las Vegas. So you can sit in your hotel in Las Vegas and watch the mushroom clouds. This was 1960. Now you're telling me that if the worst possible thing that happens at Yucca Mountain happens, that it's going to make any difference to what we have done right next door, literally 5 miles away? There's no way that's credible. No way. But you won't read that on the internet. All right, so what are we going to have to do to get from where we are? One is we have to continue to operate safely. We cannot have an accident every 10 years. That has to be ingrained in our culture. We cannot ever relax and say, we're doing great. We've got to continuously improve. We've got to get deployment of modern plants, and this gets construction, cost estimates. I've never seen anybody overestimate the cost of a project. How come we always miss in the other direction? There's got to be something wrong with the way we do economics if we always err in one direction. It can't be a legitimate estimate. Regulatory environment affects us a little bit, but I would argue the single biggest things are a stable electrical market, stable financial market, and if there's going to be any, some decision on carbon credits. Until 2007, 2008, I would have bet that the United States government would have put a carbon tax on CO2 emissions in place. As soon as the financial collapse of 2007, 2008 happened, it totally diluted all focus on greenhouse gas emissions. I don't think the government could make that decision today. And obviously in the nuclear industry, some people say that that's the one thing we really need to get from where we are to building new plants. I'm not quite that pessimistic. We need a realistic plan for waste disposal. The Blue Ribbon Commission issued the report last year. It's mostly disillusional for most of us, I think, that it was the same old, nothing new. We got to have another study. We're going to take another decade, and maybe eventually we'll do something. That's not what the public wants to hear. We have to actually do something. I argue we need to eliminate all government subsidies for energy. Nuclear is subsidized, not a very big amount, but all of our competitors are also subsidized. And I think this makes for a very bad market situation. If we subsidize anything, we're not going to make the right financial decisions. We are going forward with something based on a political agenda in many cases. So I think we need to get rid of that. All right, what do I like to see from students? Well, the one thing I keep stressing in my classes is to really understand the world that you live in. And I do have to compliment students of today. You guys know far more than we did when I was a student about the world. My world was about this big when I was in graduate school. Today, for better or worse, you guys know a lot more about the world than we did. And it does have a negative effect that it's hard for you to focus sometimes on this little bit I would like you to get done, because the whole world's out there. But I would like you to understand the realistic goals of the third world. You need to go and visit the third world, see how bad it is, and where they have to come from to get to where we are, and understand in the process what I call not a third world, but a first world problem. I think we have lots of first world problems. We are so affluent that we can sit around and think about things that most of the world could care less about. We just have the ability to do that, and we spend our time doing that. So be realistic about that, and learn how to make decisions on what's most important and what's less important. Sometimes we devote equal amounts of attention to decision making for things which will make no difference in the long run. I have spent countless hours at the Nuclear Regulatory Commission arguing about things which are absolutely inconsequential and failing to talk about things which matter. Don't stand up and say, no, that's not right. We shouldn't be doing that. Be proactive. This enthusiasm for innovation is huge. That's why I mentioned the 50s and 60s over and over again. I want to see students come out with that enthusiasm for doing things. You should say, it can't possibly take 10 years to do that. I know we can do that in 5 years. We have to have that attitude. It's got to be a can-do attitude. And don't overlook the amount of hard work that it takes to do anything, whether it's getting your degree or working at a job. I mean, it's called work for a reason. It's not always easy. We hope you have a job which is fun. I love looking up and saying, oh shit, it's 7 o'clock and I was supposed to be home at 5 o'clock. That is the best you can hope for, is every day you're late because you're so engaged in what you're doing. Enthusiasm is the thing that drives the world. So I hope you take up that challenge and do. We need people who change the status quo. We old fogies are not going to change. We are who we are, but you don't need to accept that. You are free to push for bigger and better things, and I hope you all do that. Sorry I've run over so long. I apologize for ranting on at things about which I'm not even an expert on. So thank you for your time.
Ohanian to come up, and our photographer take a picture as I'm presenting the plaque. Thank you very much. Thanks
Great.
a lot.
Thank you very much.
Thank you for coming.
Thank you again very much. Really very sorry about Jack's passing. He was a wonderful, wonderful man.